My name is Eduardo. I started working on QEMU, dealing with x86 CPU models, and today I'm the co-maintainer of the x86 architecture code and the machine core code. That's basically the common code for machines in QEMU. One question. How many liver developers we have here? Okay, yes. This talk has a focus on the interactions between QEMU and liver, so it's something I want to work with liver developers. So I will first introduce a few basic concepts about what are machine types, how they work inside QEMU. Then I'm going to talk about the current needs and current issues with what we have today, and then discuss a few possible solutions to address the issues that I'm going to talk about. So this talk has some overlap with previous talks on KVM Forum, as the Rethinking Machine Types talk from David Gibson and the QEMU Interface Introspection talk from Markus Armbruster. But I'm not addressing exactly the same issues. But it's related, but not exactly the same issue, so I need to keep that in mind. So first, a few basic concepts. Machine types are basically an abstraction inside QEMU that's exposed to the -machine command line option, and it has two different goals. So the older goal and the first goal that when they were introduced in 2005 was to allow the same QEMU binary to emulate different machines. That was really simple. When this one was introduced, it was just to allow different PowerPC machines to be emulated, I think. But today, we have other goals with this interface. That's basically keeping backwards compatibility regarding command line compatibility, migration compatibility, and gas ABI. So you could keep upgrading QEMU and keep all these things working. And they do that by hiding some things behind a machine type name. So a machine type name encapsulates the construction of basic devices of a virtual machine. It encapsulates some options related to migration stream, and lots of other defaults that you don't want to break when you upgrade QEMU. So it basically tries to hide everything behind a simple machine type name. This is how machine types looked like when they were introduced in 2005. It was really simple. It had basically a name, a description, and initialization function. All the magic happened inside that code. So it just allowed you to call different initialization functions depending on the machine type you were using. And when we introduced that, we have 5 different machines. Today, this is how it looks like. So since that time, lots of different things happened. Don't worry about understanding everything that's there. Just to compare the status today. So basically, the machines were converted to be QAMO classes, to use the QAMO object model. And lots of things that were hidden inside the initialization function were moved to the machine now called machine class object, but basically the same as before, to help reusing common code to do the same things related to different machines, and to help expose additional introspection information to the outside. And today, this thing has grown. You have more than 120 different machines, and now we are going to see the effects of that growth. So basically, today, we try to encapsulate the differences between machine types in 2 different ways. We have basically the simple way, the old way, that's basically running different code when you're using machine types. So you call different init functions. Then you have other differences that are basically inside the machine class. That's basically as data. And we have been trying to move stuff that's hidden inside that code to the machine class over time. That's why the machine class structure is so large today. But we need to keep that in mind when we are going to address these other issues. So that's it. That's what the machine types do. They just run different code, implement different behavior depending on the machine type you are using. And what are the current needs we have or current issues we have? When I'm going to talk about current needs, I basically focus on libvirt. And the starting point to see what are the current needs was to take a look at the libvirt code. And this is what I have found. So I grabbed libvirt to code that checked the machine type name, trying to figure out something. And what I found was lots of cases where machine types were hard-coded inside the QEMU code. So it basically shows that the abstraction has failed. It's not hiding those details. It's basically trying to hide it, but libvirt is trying to extract that somehow, and they don't have that information. They just need to check the machine type name. That's all they have. And many of these cases are inside helper functions that are used elsewhere. So some functions are basically trying to check what's the basic family of the machine type. Some of the helper functions are trying to check for specific devices or specific features of the machine type. So this is what shows what libvirt needs and what we are not providing to them. And so before I try to address solutions, let me show you how exactly libvirt is communicating with QEMU. So basically, libvirt runs QEMU at two different moments. This is a very simplified model. So if I'm wrong, libvirt developers could correct me and we could discuss that. There are two. So libvirt runs QEMU when initializing to check what QEMU is capable of doing. So it starts QEMU using machine own, and it makes a few questions to QEMU, through QMP, using a few different commands. There are some query commands. I will focus on query machines, but there are others. And it saves that on a cache, that the QEMU capabilities cache. And when we are going to start a VM, libvirt is going to run QEMU again with all the right parameters depending on the VM config, and then you have a VM running. The issue we have here is that this data that is returned here is not complete. That's why libvirt has all this code that tries to deal with machine types. And another issue, I'm not sure we can say issue, but I see that as an issue, is that before QEMU started here, there's no data flowing from QEMU to libvirt at all because QEMU is not running yet. So if you need to ask QEMU any questions before running the VM, you have no opportunity to do that. So a little bit about query machines. The query machines command is really simple. It simply returns a list of machine info structs. It's a QMP command. And it returns a really tiny, a really small subset of the machine type information we have inside QEMU. So we have all these fields inside QEMU, and today we have just 5 fields. So that's a really small amount of information we have here. But, okay, extending query machines is easy. I don't know why we don't do that today, but it's supposed to be easy. So we just move data to machine class if it's not there yet, and you add new fields to machine info, and libvirt can ask for that. So that's supposed to be easy. But I believe there's some information you can't return that way. So just to summarize what kind of queries you might want to do to make to QEMU. We can ask for stuff that depends only on the QEMU binary. You want to know what the QEMU binary is capable of doing, which QMP commands are available. You may want to copy a schema that's what related to Markus talk from last year. And this thing is already working. It's already available. Then you might want to ask something that depends only on the machine type name. And we have query machines, and it's supposed to be easy to extend. I just don't know how much that can grow, but it can still make it grow. I don't know for how long. But now we might want to ask libvirt for stuff that depends on the machine type and machine options. And machine options include the accelerator, either you're using KVM or TCG, there may be some differences, and stuff like that. And you can ask QEMU for that information because QEMU is not running yet. You can ask questions just only before you start the VM, only the very beginning. You don't know what the options you are going to use, and you can query that. And the same happens if you have any information that depends on other options. And you can ask QEMU for that. So I'll try to give a few examples of things I think that may apply to case 2 and 3. And on some cases, we may try to move information to category 1, but we need to see if we can do that or not. So one example here is CPU slots. So basically, today we have CPU hot plug, and we model CPU hot plug as just adding devices to the machine using device add. When you do that, we have a command called query hot pluggable CPUs that tells us where exactly you can plug CPUs, what are the valid parameters you can do that, where you can do that, because on some machines you can attach vCPU threads directly. On some machines you can attach only entire sockets, and you need that information to be able to know what can be hot plugged. But what if you want to do the same for non-hot plug CPUs? And one of the things we have been trying to do is to move the SMP configuration to something that's closer to the other devices. But how exactly do you know what are the available sockets on a machine if you didn't start it yet? So on this case, it's on PC, it's quite easy. You have sequential sockets. But on these sets of sockets or available CPU parameters depend on the machine, so you need to ask the machine for that. Another example, I think this is the most complex one, is address assignment. So address assignment code, the set of addresses available where you can put devices on QEMU depends on both the machine type, the default devices you have on the machine, the buses you have on the machine, and depends on all the other devices you added to the machine. The solution we have today is that libvirt duplicates all the logic that's implicit inside QEMU for address assignment inside libvirt code. So we have this file, QEMU domain address.c, that's basically a very large collection of special cases that tells us, okay, what addresses are available, what are the rules depending on the machine type. So for example, this is from that file. It has some code that needs to check, okay, is it using a i440 machine? So we need to validate the addresses using those rules. Are you using a Q35 machine? You need to validate the addresses using those other rules. Then it gets more and more complex. So I have other cases. So if you're adding a serial port and you're on a P-series machine, then you need to know that the device type of that the serial device is going to use the SPEP VIO, so it's going to use an address. So you need to take that into account. and do that, allocate an address to the serial port. All because we can't ask QEMU. QEMU is not running yet. So those are the issues I want to address. Now about the solutions you might have for that. So back to the way QEMU is run by libvirt, and they communicate. One solution is to, okay, let's run QEMU and ask the questions you need, ask all those questions, and then run QEMU again and start the VM. The problem with this is that libvirt, we are trying very hard to reduce the boot time of VM. So libvirt does not do that because you don't want to all the latency involved with loading QEMU again, asking those questions, and then restarting it. Another solution we may have, that's what I'm going to propose, and I want to hear feedback about that, is that you could have a mechanism that could allow you to ask QEMU questions before configuring the VM. This way you could have, let libvirt have all the information you need that couldn't be queried at the very beginning, and then you could configure the VM and start the VM, and the problem would be addressed. The only issue with that is that we will need to change some things inside QEMU. So this shows how initialization works on QEMU, and that's probably one of the reasons we don't have something like that. Though basically, when QEMU is started, it's going to parse the options, initialize the machine, and then execute it on the QEMU main loop. Only when you start the execution phase, the monitor is going to be available for querying. So that's too late. You can ask more questions that would allow you to configure the machine correctly, because the machine is already initialized. Another issue is that all these steps sets global variables everywhere instead of just having a single place where everything is configured. But that's something that we need to address. So we would need to extend QEMU to do something like this if you want to make QMP available. So we would need to start the QEMU main loop before the machine is initialized, allow QMP queries to be made, then allows VM options to be set, and then you can ask QEMU to proceed with initialization. I add a question mark here because I'm not sure how exactly we would configure that, but we would need to set some options somewhere and then initialize the machine. So to proceed with that, what do we need to do? So first step is we need to enumerate what we are not providing to libvirt and libvirt needs. This is something, I took a look at the code, found some cases, but it's not, I didn't check every single place where information is lacking. Then we can extend query machine, so that should be the easy part. There are some cases where the new solution I'm talking about is not necessary. And some people might even argue, okay, you should never need that, and everything should be available before you start QEMU on the probing step. And then we need to design new QMP queries for all that information. I'm saying this is hard, not because it's necessarily a hard task, but because it's going to involve designing the interface, discussing with libvirt developers, QEMU developers to find what's the proper way to do that. So it might take a little while. And then we could implement something that could allow queries to be made before initializing the machine. So we would need to make the monitor available before machine needs, like I said. And we would need to implement comments that would allow options to be set before starting the VM. I think that's doable. So I want to hear feedback and see what are the choices we have when doing that. A few open questions we still have is how exactly we are going to configure the VM. So today we have the command line. We need to map that to QMP command somehow, and what abstractions we are going to use for that. Because today we have a few different abstractions to represent configuration and inside QEMU. We have QEMU ops that basically represents configuration options in a generic way. You have QAMO abstractions that basically is completely separate, not completely separate, but have their own abstractions on interfaces to check what's available. We have QAPI, the Q API, that's separate from the QAMO abstractions, that have their own way to represent what's available, what can be set, what can't be set. So how we are going to model that? And one big open question is how exactly we are going to encode those complex rules, especially the address allocation rules. Can we represent that as static data that's available in the very beginning, or should we make something more dynamic that would need to be queried later based on the VM configuration? So we need to find ways to encode that instead of just duplicating logic in QEMU and invert, and this is probably the hardest part. And one thing we still don't know is how much exactly can we make query machines grow? Because today it's very simple fields, but can we encode the machine and buses and all that information inside the query machines, or do we need new query comments? This is related to the second item. I mean, what can be included in query machines, what need new abstractions? So this is basically the proposal, the open questions I have, and I hope we are going to figure this out soon. And after we do that, we may even consider this is something I have been thinking about. So can we use this mechanism to avoid having to run QEMU at the very beginning to ask for capabilities, because you could just ask when necessary? Can we use that to make better, more machine-friendly, not machine-like in machine types, but machine-like software-friendly error reporting when initializing a machine using the new interface? And there's this item about splitting the machine initialization and execution, because this is related to the David Gibson talk from last year about we could make the default devices available in a more abstract way, so it could be used or stored, delivered, or whatever. This is something I'm not addressing here, but it could be a step. And this is something I remember when people introduced machine node, one of the ideas was you could start QEMU with machine node, create all those devices, link everything, and you could have a working machine. And this is far from being possible. But do we want to do that? Do we want to make sure everything related to machine types could be represented as data somehow, as just a device tree somehow, so we could save it somewhere else and load it instead of being represented as code? This is something, actually, this is one of the things I wanted to address, and then when preparing the material, I noticed, okay, we need to tackle those basic issues before we try to cover the entire world. So this is it, and thank you for your attention. Questions?
Until now, it was basically like this, that at one point when we were able to stop QEMU, for example, with minus uppercase S, all state in QEMU was fully initialized. So in order we could like just assume that certain stuff was there. If we know, like, don't fully initialize everything, that would mean that, for example, certain QMP commands could suddenly break, for example, because there are no virtual CPUs.
Yeah.
The thing is, do we really want to spend the effort and all the involved complexity just to avoid maybe in the end starting one additional QEMU instance for probing on the libvirt side?
I think I'm not the right person to answer that. Do you have a libvirt developers who could explain the issues? I mean, I know this is a problem. I know we don't want to restart QEMU multiple times, but I have seen that libvirt never did that. And one of the reasons, so it's my limited view, seems to be startup time. But we have other reasons to that.
Startup time, but also the additional setup we are always doing to prepare QEMU for running, not even when it would not run. Also, I'm not quite sure whether there is, but there might be data that you would that still you would not be able to query before, or you would need to make multiple iterations of this, so that because you set up something and another data depends then on something else. So,
I hope you are not going to have cases like that, but it might. For example, device addressing is an example. So when you add one device, the available addresses is going to change. Then you add another one. So if we need something more iterative, I'm not sure we really need it, but it would involve running QEMU multiple times. So it's one limitation we would have.
Exactly. I just want to make everybody aware that simply doing such things could involve a lot of complexity on the QEMU side. For example, also if we would want to ask a running QEMU instance, for example, what does it look like under different accelerators? With one running instance, they could be done, but the complexity involved may not be worth it. So that's the same thing here. That's just my comment.
There is another reason for wanting to do this. As is, we do many things two ways on the command line and in QMP. It's kind of redundant, and there's this long-standing dream of just starting QEMU with next to no options at all, an empty board, and plug in everything, configure everything over QMP. Once you can do that, migration becomes much simpler because you can transfer the configuration via the migration stream. And the whole class of problems where source and destination need to have exactly the same options, unless you know what you're doing, and then they can be slightly different, that all goes away.
Yeah, so just try to illustrate that. I didn't mention that, but this is one different here. So today, when you're configuring the machine, option parsing configuration affects lots of... I'm using global state as something meaning, okay, there are global variables everywhere that you don't know where they are. And it's going to affect that, and you don't know where it is. If we do that, option setting is supposed to affect one thing that is tracked at the same place. It might be QEMU ops. I don't want to say it's going to be. But I don't think we need to use, let's discuss that later. So it's going to be in one place, and can be transferred more easily. I think that's what you're talking about, right?
Yeah. QEMU ops and QMP don't mix well. I know because I screwed it up myself a couple of times. It would be wonderful if the command line could be quapified, but it's a really big job.
Yeah. Maybe I'm seeing QEMU ops as something different than not an interface, but just as a place where you put this stuff, because we already saved that stuff there.
But that's not what it is. It also parses. And if
we should remove the parsing, just use the saving part. But maybe it won't be QEMU ops anymore. It's going to be something different. Yeah.
We need to talk.
We need to what? Okay. Thank you.
So I think... I think another question is how broad you want to make a scope of this. I think it would be easier and you could get the most useful of this if you're limiting this to the guest, all the options affecting guest state. for example, dash device and everything what comes at
Yeah.
the state. And we have dash drive for the hardware, for the host side configuration, also user interfaces. And I think it would be a bit easier to get this going if you're just doing the guest state, and also I think that's where the most machine-specific stuff is involved, and also which is most interesting for the migration use case.
That's true. We don't have this separation today. We have just options.
Yeah, it's pretty mixed right now, yes.
Okay, we are out of time.